My people, this is the second video for trigonometric integrals. In the last video, we did several examples that were based on sine and cosine and powers thereof. In this one, we'll get on to other ones most likely, but I want to finish out with a couple more examples using sine and cosine. This one is a little more pressing because in the last one, in the last two, one of them was raised to an even power and the other one was raised to an odd power. And when that happens, we recognize the fact that the odd one, the one raised to an odd power, is going to leave one of them behind in order to make your du for your eventual u substitution. In this case, neither of them are odd, which means that I need to figure out a different strategy, okay? Now, remember that I talked about the power reducing formulas, the IDs. And remember that if you don't remember which is which, remember that they come from, and let's go ahead and look at them real quick. Let me flip back for just a second. They come from the double angle for cosine, right? In order to basically get the power reducing for sine, you take this one and just solve for sine squared. So let's do that. Or let's start with the cosine one since I've already put a 2 down. All right, cosine squared x minus 1. Well, that means that if I'm solving for cosine squared, I'm going to go ahead and switch sides right here as I'm adding 1 to both sides, equals 1 plus cosine 2x. And cosine squared x is equal to 1 plus cosine 2x over 2. Well, something similar happens with cosine 2x is equal to 1 minus 2 sine squared x. Now, eventually, I'm going to have to divide by that negative 2, and I don't want to. So let's go ahead and multiply through by a negative. And when I actually change sides, I'm going to, as I'm adding 1, what I'm going to get is 1 minus cosine of 2x. And then, of course, I get sine squared x is equal to 1 minus cosine of 2x over 2. Now, this is going to be helpful. And in the first round, it really doesn't matter which is which, right? The reason it doesn't matter which is which is you have one of each. And so let's go ahead and change the form of this integral by plugging this in for cosine squared and this in for sine squared. Well, that shouldn't be, and in this case it doesn't really matter because as long as you have both of them there, then you're good to go. Okay, well that means that I get 1/4 out in front because I don't want to deal with the fractions inside the integrand, and that of course is going to be the difference of two squares, and it winds up being cosine squared 2x dx. Now it matters which one is which because I now have to use the power reducing again, but instead of cosine squared x, it's cosine squared 2x, but it's the same relationship. I just have to have 1 plus cosine 4x over 2. And so let's go ahead and see that. I'm going to keep it all as one integrand right now, all as one expression. So 1 plus cosine 4x over 2. Now, of course, you need to be careful because this numerator right here is functional parentheses, and you're going to want to basically be careful that you distribute this negative across that binomial when you break that fraction apart, which you should, right? And you get 1 minus 1/2 minus 1/2 cosine, so that's not supposed to be 2x, it's supposed to be 4x dx. Now you've used power reducing twice, and you should get a good result. This, of course, right here is just going to turn into 1/2, and so you have 1/4 times 1/2 dx minus 1/4 1/2 cosine 4x dx, and of course we want to simplify that. We'll do 1/8 dx minus 1/8 integral of cosine of 4x dx. And basically I've gotten to something now that is integrable, but I didn't do it by means of Pythagorean because I couldn't. If I'd done it by means of Pythagorean, I would have gotten an integrand, an expression in the integrand that was all in terms of cosine or all in terms of sine, and there would have been nothing available to use for my du. In this case, I get 1/8 x. Cosine 4x is the derivative of 1/4 sine 4x. And so the 1/4 will combine with the 1/8, and I'm going to get 1/32 sine of 4x plus c. Now, the question is that the only way to do it? And the answer is no. Okay, let's go ahead and look at another way to do the same thing. Now, there is another identity that can be used when you see sine and cosine together. But these are both squared, but it doesn't matter, okay? So what we want to do is use our rules of exponents to basically make, instead of sine squared and cosine squared, make it the product of sine and cosine, the whole quantity squared. Now this has the beginnings of a double angle identity, and therefore you can just go ahead and put in 2. Now that is not a 2, that's actually a 4, so to compensate I'm going to go ahead and put the 1/4 out here. Now the moment that I've done that, okay, I'm going to have 1/4 the integral of sine of 2x dx, or sine squared x, sorry. Now from here I can use the power reducing for sine, and I'm going to get 1/4. And remember that the 1 for sine is going to be 1 minus, okay? So 1 minus cosine of 4x, all of that over 2 dx. And what I get here is I get 1/8 integral of 1 minus cosine 4x dx, and that is going to get me exactly what I had in the last one. I'm going to get 1/8 x minus 1/32 sine of 4x plus c. Now, what you might have noticed in the middle of that, in the middle of the last version, is that once I got to here, I didn't actually have to use the power reducing again. I could have just used the Pythagorean to change that into sine squared of 2x. I missed it because I was just going too fast and I was in the mode of doing the power reducing. But either way, you're going to get to the same answer. Now, using the Pythagorean instead of doing again the power reducing and have to deal with the distributing the negative and all that sort of jazz, it would have been more efficient. But showing you that it can be done both ways, I think is instructive. So there you go. Now, let's get down to this one down here. This is of the same logic. Now the 1/2 exponent might attempt to distract us, but it shouldn't distract us, right? Because I'm still interested in what I can change into the other trigonometric function and what will be left over when I do. Sine to the 1/2 x obviously is not going to be changed into anything. Cosine cubed, however, can be pulled apart into cosine squared. So let's go ahead and do the sine to the 1/2. Let's transform 2 of those into 1 minus sine squared x. You're left with cosine x dx. And despite the fact that I'm going to have fractional exponents, who cares? Fractional exponents can still perform inside u sub and can still give me, can still basically be legitimate u values, right? And so just instead of integer exponents, I have rational exponents, but it's still u to the 1/2 minus u to the 5/2 du. Okay. Well, if that's the case, then I know I'm going to get 2/3 u minus 2/7 u to the 7/2 plus c. Okay. And you can change the form of that and clean it up a little bit. You know, if it was in the back of the book, it might be something like, you know, take all of the fractions out. So basically treat this like it's, treat them like they're common denominators. So treat this like it's 14 over 21 and this one like it's 6 over 21. And therefore, if you pull out 2 over 21 and then pull out the sine to the 3/2 x, what I wind up being left with is 7 minus 3 sine squared x plus c. And, you know, textbooks oftentimes put the answer like that in the back of the book, but all it is just a clever factorization of the terms that you're left with after the integration actually takes place. So there you go. Now what we're going to do now is we're going to move on to similar problems that deal with tangent and secant. Now remember, the great thing about sine and cosine is they are not only related by differentiation, but they're also related by Pythagorean. Well, the same is true of tangent and secant, but you wind up being just a little bit more difficult, largely because the derivative, your du, is going to require two trig functions because the derivatives of both secant and tangent are second degree. Tangent is secant squared and secant is secant tangent. But the overall strategy is still the same. You still need to be looking at it and thinking to yourself, how in the world do I change the form such that I have a legitimate u value, but what I've left behind to combine with the dx leaves me a legitimate du. And here's the thing, it winds up, you can just play around with it. Tangent and secant. Well, I noticed that tangent is only a part, is only one part of one of the derivatives, right? And so basically, if I rewrite this as secant to the 4th x, and then secant x tangent x dx, I now have u to the 4th du. And that's, you know, kind of neat. So basically what I need from here then is simply just a 1/5 secant to the 5th x plus c, because I didn't even have to use any IDs. I simply had to factor it creatively, or factor it correctly, in order to reveal my u value, in this case raised to the 4th power, and my du. Okay. What we're going to do on this next one is we have tangent squared and we have secant squared. Okay. Secant squared is already a derivative, so basically that's already a du. I don't really have to change anything. So I already have u squared du, and so I might as well just go straight to 1/3 tangent cubed x plus c. Now, of course, they can become more difficult, and they will, but, you know, on something like that, it winds up being relatively easy. If you had been given, alternatively, instead of that, let's say that you were given tangent squared x and then secant to the 4th x dx, what would you do then? Well, I would basically, you know that you can't have secant tangent as the derivative, because if you pull one secant and one tangent out, then they both wind up being odd, and you can't change one of them into the other. Okay, because in order for secant tangent to be the du, I mean combined with the dx to be the du, I would need, after I pull it out, to have tangent still raised to an even power. But in this case, it's not. So what I need to do is I need to take one of those secant squareds, and I need to transform it into tangent squared plus 1, leaving the secant squared x dx. And that right there is my du, and I'm left with tangent to the fourth x plus tangent squared x. That's basically u to the fourth plus u squared times du. And this then becomes 1/5 tangent to the fifth x plus 1/3 tangent to the third x plus c. Okay, well, let's say, just for argument's sake, that it was tangent cubed x and secant to the fourth x dx. Well, in this case, you actually would be pulling out a secant and a tangent, because once you pull out the secant and the tangent, you have secant cubed x and tangent squared x and secant x tangent x dx. Now you actually do have the possibility, because tangent was raised to the third, so when you pulled one of them out, it left you with a viable tangent squared that allows you to use your Pythagorean. And of course, the Pythagorean for tangent squared is secant squared x minus 1. And this becomes secant to the fifth x minus secant to the third x. So that's u to the fifth minus u cubed. And this right here is, of course, your du, at which point I get 1/6 secant to the sixth x minus 1/4 secant to the fourth x plus c. And that basically that basically is how that one is done. And the only subtle difference between the two was just 1 degree of tangent. But that 1 degree of tangent threw the whole thing off, because it dictated whether I had a viable Pythagorean identity once I pulled out a particular pair of trigonometric functions to create my du. Okay. Now, let's actually deal with a nasty one, and then this will probably draw to a close our discussion on this video, and then we'll sort of move on from there. If we have secant cubed, and actually we may need a separate sheet of paper for this, but let's see. If I have secant cubed, obviously that can be pulled apart, but if you're looking at it, you should be having a little bit of trouble with what it is that we need to be doing here. Because if I pull out a secant squared, it's secant times secant squared, and sure, I have a du, but it's not the appropriate one for the u that's been left, right? So if I pull out secant x and secant squared x dx, that might be a legitimate du, but only if there's a tangent sitting right here, or something that I can turn into an expression in terms of tangent. In this case, I can't. But what I can do is I can use parts. So right here is going to be my dv. So let's let u be equal to secant x. My dv is equal to secant squared x dx. I didn't leave myself a whole lot of room, so this may go on 2 levels. Secant x tangent x dx. And my v, of course, is going to be tangent x. Let's see whether that actually gives us any traction, okay? Well, if I do that, then what I'm left with is uv, so secant x tangent x, minus secant x tangent squared x dx. Well, at this point, I don't want to do parts again, because I actually do see the fact that that tangent, we can actually transform it. And you're like, well, what use will that do? Patience, okay? I'm going to show you. So tangent squared becomes secant squared x minus 1 dx. And at that point, I'm going to get secant x tangent x minus secant cubed x dx plus the integral of secant x dx. And you're like, oh my gosh, will you look at that? I can add that, since this secant cubed x is understood to be over here, I can add that to the other side, secant cubed x dx, and that leaves me with secant x tangent x plus, and of course the derivative of secant is the natural log of secant x plus tangent x plus c. And then to get to the actual answer, all I really need to do is I need to divide both sides by 2. And I'm left with 1/2 secant x tangent x plus natural log 1/2, secant x plus tangent x plus c. And of course, you did distribute the 1/2 to the c, but you know, c, some random constant, times 1/2 is still some random constant. So there you go. On the next video, what we'll do, oh, by the way, this will be helpful if you were to do like secant to the 5th as well. You would use the same strategy, but of course it would be a little bit longer. You'd have to sort of pull it apart a little bit more. But you'd use roughly the same sort of strategy for that. We will start in the next video on some cotangent and cosecant and just some other random style of problems, sort of a mixed review, and that will take us into the realm where we need to start doing definite integrals as well. If you have any questions, as always, shoot me an email. Bye.